morning. Questions? Next week on Wednesday, I leave for MS&T a little early. But I think we have class because I think timing-wise it works out just fine. I can't remember what time my flight is, but I don't know that. But I will know it on Wednesday. I'll let you know on Monday if we have class. And my intention is to have an exam the following week, right? Who's going? Anyone here going to MS&T? You are. Okay. So my intention is to have the exam that week, unless I'm not here Wednesday. If I'm not here that next Wednesday, which is today, then we'll have the exam that. Good. Any questions? Okay. Talking about clay characterization, and essentially we talked about sedimentation behavior. If you think about clays, they offer somewhat a unique opportunity for characterization because of their nature. They are sheet silicates, they have water with hydration, etc. Simple things like LOI, loss of ignition, is really effective as a way to have an understanding of the clay. And they are a mixture of clays and quartz, typically is our assumption. And we went through that discussion on Monday, right? And as a first approximation, you can get pretty close to the free quartz content by simply doing LOI and making an assumption. What's the assumption? So to use LOI, right, to estimate the amount of free quartz, you make an assumption. And that assumption is?
Clay impurities, silica.
Yeah, right. All you have is clay and quartz. Okay? You know that's not true, but as a first pass approximation, it's pretty good. Then we have thermoanalysis is great. Thermoanalysis will tell us when those impurities burn off or when the waters of hydration come off. Chemical analysis is really useful. And when I first started doing this 25 years ago, I thought that the chemical analysis was sort of interesting but not very useful. And now we've come around where the only thing we really need to know is the chemical analysis. And that's not true in terms of clay characterization, but in terms of predicting what will happen in firing, all we need is the chemical analysis because it tells us then the amount of alumina, the amount of silica, the amount of fluxes in the system. And the rest of it, iron and titanium, we really don't care about. You remember our discussion about titanium, right? Why is it important? Color. Because it controls the color, right? So you get the titanium metal, you have the color. This cation exchange capacity, I'm going to come back to in a second. Density by helium pycnometer, you know, I mean, it's a useful tool, but not very important for us for clays. Specific surface area is very important, and we're going to talk about that next. And because we use it for dispersion behavior, and so you should, if you're not familiar with specific surface area or how that works, you should become familiar with it. And I'll post these slides to Canvas. X-ray diffraction for mineralogy, and then particle size distribution by sedimentation through setograph or laser scattering. And if you've been in my classes before, you know that I don't like laser scattering. Let's see how to put that. I don't like it at all. Why? Yes?
It's not accurate on the smaller particles.
No, actually, it's probably pretty accurate on the smaller particles because it uses either Fraunhofer diffraction or Mie scattering, M-I-E, excuse me. Scattering, and you can then, that's good for small particles. The problem is that laser diffraction or laser particle size analysis requires diffractive index. Okay? And what you have in a typical clay is a bunch of minerals, right? You don't just have kaolinite. You have kaolinite and quartz, okay, that's two. You frequently have smectites and montmorillonites. You have titanium, you have iron. Has particles typically in that system. Not all the iron is in the titanium. You can tell that from the chemical analysis. But when you get all done, you're making an assumption about the refractive index. That then affects your ability to measure particle size distributions. Everyone has gone, not everyone, but most people have gone to laser scattering, and the problem is those assumptions don't go away. Each instrument manufacturer has developed their own algorithm to look at the data, right? And that means that when you get data from one company, it may not match data from another vendor for particle size distribution. We have micromeritics instruments. I like them. We have the X-ray cetograph, and we have the laser scattering device, which I think is not working right now. And they use garnet as a standard. I'm very impressed by that because you run garnet in the X-ray cetograph, and you run garnet in the laser scattering instrument, Saturn or whatever it's called, and it gives you the same mean. Yes?
How does TGA work?
I'll get to that in just a second. Is that okay? So, I accuse them of taking a page from Volkswagen. If it says garnet, this must be the particle size. Anyway, he didn't appreciate that, by the way. But the distributions are different and they don't match, and I have a problem with that. The benefit of laser diffraction is it's fast. The downside is I don't trust the data, so what's the point? Anyway, but X-ray sedimentation is excellent. Let me go back a page here and see what we have. So there's a group, Teal Kalen there in Georgia, and they mine clays for the paper industry. We talked about that, right? Most of the clays that are mined in the United States, vast majority of like 90% go to paper, something like that. Okay. This group at Teal Kalen, they had a couple clay mineralogists. They were really quite good, and they worked with another company. I can't remember the name of the company. Did a lot of characterization on clays, and this is what they obtained by looking at X-ray diffraction, separating out fractions of materials, etc. 88 to 95% kaolinite, a trace to 5%. This is in the kit that we were looking at. You get mica, smectite, iron oxides, and it takes a rutile, which is TiO2, and others, and it's a pretty decent breakdown. So let's go this way. We did LOI, not to do surface area today. So here is thermoanalysis. So TGA, the way that it works, is essentially you have a balance and you have a small sample. Typically the samples are very small, and what you do is you monitor the mass of that sample as a function of temperature. So your x-axis here is temperature, and this is DTA, sorry. We'll get to that in a second. Here's TGA. So you look at the weight loss of your sample. This is a sample mass and a percent, so it's weight remaining, if you will, or mass remaining. And then you monitor that as a function of temperature. So it's a great instrument. Next semester, not next semester, B block is we're piloting in a new lab in ceramic engineering thermoanalysis. Okay, you can still sign up for it, I think. We could probably get you a waiver on the late ad. It's a 1-credit lab course. It hasn't been offered in a long time. We're sort of developing the course from a different perspective, from scratch. You may be familiar with that. We're starting to pilot a series of 1-credit labs that are half-semester labs with 1 lecture and 1 laboratory exercise each week during like A block or B block. So thermoanalysis is B block this semester. And we will go through TGA, thermogravimetric analysis, differential thermoanalysis. We will do heat capacity or heat transfer. We will do dilatometer, etc. We will do all these things. Thermoanalysis is a great tool because what you can do with thermoanalysis is you can actually use it for mineral identification. In conjunction with X-ray, you can get a very complete picture of what's going on because different minerals lose mass at different temperatures, or they have chemical reactions or crystallographic changes, say polymorphic transformations that occur at different temperatures, and you can pick them out. So what you have here is weight loss. These are the KGA1A and KGA1B. Those are the source clays from the Clay Mineral Society. Okay, and I did those as an example. Okay, so poorly crystallized kaolinite, you see that there's a small difference in when those waters of hydration come off. So what you're looking at is in this structure for kaolinite, right? We don't actually have any water. What we have are OHs. And these OHs, though, come off as water. So when we heat the structure up, when we heat the sample up, you'll start to evolve water by the decomposition or the breakdown of the structure. And what you get back is metakaolin. And metakaolin is occurring, by the time you get here, 700, you have metakaolin. It's all metakaolin. Okay, we use a small sample size. Well, I should ask, why use such a small sample size? Our sample size is typically about 20 milligrams, which is small, right? 0.02 grams. Why so small?
Such a uniform heating throughout the whole sample.
Yeah, to avoid heat transfer problems, right? So you typically have a platinum pan, contact with the thermocouple, and you heat the sample and it monitors that mass as a function of temperature. If you have a large sample, the outside is hot before the inside is, potentially, right? And then you get a heat transfer problem. You see here that there's a temperature range over which that dehydroxylation takes place. And it's not particularly broad. You can see where it starts and where it ends. Okay? And you also see, this is what's nice about TGA, is up here, somewhere around 100 or so, you have a small weight loss, which is associated with water, physically bound water that comes off the atmosphere. If you dry the sample, that potentially goes away. We're pretty close here. Okay? If you don't dry the sample, it's a significant change at 100 degrees or so. And that 100 degrees is approximate. Now I know water boils at 100 degrees C, but the fact is this is physically absorbed on the surface of the particles, okay, potentially condensed in small pores between the particles. That water comes off first, physically absorbed water comes off second, and maybe a little bit greater than 100 degrees C. Okay? Chemically bound water, on the other hand, may be much hotter. So Bill, of course, did a bunch of work. The student's name was Yoon, and Yoon looked at frits for glazes. And what he found was that the frit reacts with water, and it actually exchanges water, H3O plus, for sodium, for example. Those waters of hydration come off around 850. So it's really hot. Okay, so this is TGA, and then this is DTA. So the way that DTA works is a little bit different. You have two crucibles. Typically, you have a small two small crucibles. These are also small, 20 milligrams. Okay. What you have is you have a thermocouple in contact with both crucibles. All right. Now, really well done DTAs. The sample is actually embedded around the thermocouple, so you have intimate contact with the thermocouple. We don't like to do that. Actually, we really like to do that, but we don't do that typically because if you do a glass, for example, when you're done, you cut off the thermocouple and you remain B, right? Because it gets embedded in your sample. Other samples work really well, but typically platinum pans, okay? One sample here, this is called a reference, and then this is your sample, okay? And what it does is it compares the temperature between these two. Good? Have you seen this before? Where did you see it?
I did them at work.
Say again?
I did them at work.
Ah, but not in class.
It's the same thing as DSC, right?
Similar. DSC is then it's monitoring the amount of energy placed into the furnace, right, to change the temperature of the sample. Okay. Glass people, for reasons I'm not quite sure about, use DSC. We do DTA. I don't think the results are different, but maybe we'll find out. So what you do is you're comparing your sample to the reference. Okay? So you're comparing the temperature of your sample to the reference. So things that, things such as decomposition, melting, etc., things that result in a transition from more order to less order structurally are endothermic. They give off heat. Okay? But excuse me, they absorb heat. Things that go from poor order to better order structurally, they are exothermic. They give off heat. So what you get in this curve is that things like the decomposition or evaporation of water are endothermic. They require a lot of heat. So here's a question. Why do I see a small peak here? What a great question. So, if you're losing water that's associated with, say, physisorption or water in the sample, right, you would expect that peak not to be exothermic, which it is in this case. So exothermic is when the peak goes up, endothermic is when the peak goes down. We have a small exothermic peak here. Why? What do you think? Normally, you would expect that the evaporation of water would be endothermic. This suggests that the evaporation of water would be exothermic. The reason is that in this example, the reference had absorbed water. So what happens is that when it evaporates water from the reference, the temperature of the reference goes down in relation to the sample. And since you're looking at the change in temperature associated with your sample, it makes the appearance that the sample temperature goes up. So it's actually an error, a setup error, or it's an error in sample prep, if you will. Okay. Then when you get over to somewhere around 500 degrees C, you see a large endotherm. Okay, and that endotherm is associated with two things. Give me one.
The water.
Coming off of the clay structure. The other thing it's associated with, and it occurs at 573, will be the transition of alpha quartz to beta quartz. That's also endothermic. But it is obscured by the endothermic peak associated with dehydroxylation of the clay. So if you want to see how much free quartz is in there, you can get it from thermal analysis. The Orton Foundation developed this test, and as a standard test for determining free quartz level, because of requirements to reference free quartz levels or the presence of free quartz in clays, because of OSHA requirements regarding silicosis in clays and quartz inhalation problems associated with health issues associated with SiO2. Okay, and the way that you do it is you would heat it up, you go past this the dehydroxylation temperature, and then when you cool it down back down, you monitor on the way back down, and at that temperature you would have an exotherm associated with the transition of alpha to, or then beta to alpha quartz. So you get an endotherm on the way up, you get an exotherm on the way down, because beta quartz then gives up energy to go to alpha quartz, and by the area under that peak, you can determine how much free quartz is in there. So the Orton Foundation developed a way to do that. We didn't do it. We didn't monitor it back down. What's the big peak at 1,000? So, sharp peak. Good? Okay. Sharp peak, large, suggests that it's an energetic result. What do you think? Melting? Trick question, sorry. Melting is endothermic. This is clearly exothermic, right? You give off a lot of heat. That is the crystallization of spinel or molite, depending on how you look at it. Okay, so you take clay and you heat it up, it forms molite. It does it around 980 degrees C, okay, and that's that sharp exotherm that occurs at that point. Make sense? Okay. The data here suggests that there is a small difference in where these events occur. Not so much the event for crystallization for the dehydroxylation based on the structure or the degree of crystallinity of clay. I don't care about that. Okay. Clay mineralogists care about that because they're trying to figure out what clays are. But we don't really care about that. So that dehydroxylation when it occurs at 600 gives off absorbs a lot of energy, and then you get crystallization around 900. So that's what happens in clays. Yes?
Is the y-axis measuring the difference between like the furnace air temperature and the sample on the pan?
It's measuring the difference between the reference sample and the...
Oh,
Right, so it's just looking at that, not the temperature of the air. So it's looking at the comparison. So ideally, these two would have similar mass, right? And then what you're monitoring actually is, this should match the furnace temperature, that would be ideal, right? And in DFC, you're monitoring then the amount of energy that goes in to the sample, okay? And that's the difference, okay? We went through this a little bit already, and I'm not going to spend too much time on this. This is the discussion about crystallinity. It's called a Hinckley index, and looks at the ratio of these peaks. And this one here is fully crystallized. I'm not going to worry about that. But where we are here, let's see if I have anything else. We did the sedimentation stuff yesterday, and the opportunity to do that. So refraction. Good. So this last part here, raw material dissolution, we're going to get to. So you put clays in water, and anything that's soluble in water comes off, okay, dissolves. Some clays have more to dissolve than others. And what we find is that there's typically a ratio to the amount that dissolves based on the amount that you measure in chemical analysis. And by and large, it's about 1.5%. So if I put a clay that contains a small amount of calcium, for example, about 1.5% of that calcium will dissolve into the water. There are a few clays where that species that brings the calcium is highly soluble, and you see high dissolution levels. Okay? But typically what happens when you put clays in water, you get some dissolution. That result of dissolution is called aging, and we're going to talk about that. There's a lot of folklore around aging. So where I want to go next is colloidal behavior. Okay? And this is a big deal for clays. We'll go through the whole thing, okay? Factors controlling suspension rheology. You probably know by now there are 5 of them. You've been in my class before. You've all been in my class before. Okay? And then we're going to talk about colloids in general, and then we'll get into the colloidal nature of kaolin. And I'm going to make this relatively quick for the introduction of colloids. There are 5 factors that control suspension rheology. Most important is the particle-particle interactions, particularly for clays. So where we are in this process is we really don't care much about the quartz or the feldspar because they are large particles, low surface area. The clays dominate the behavior of this material in water, okay, porcelain bodies in general. Everything is controlled by the clays, okay? You need to know the 5 factors that control suspension rheology because you're going to see it on the exam. It's going to say something like, list the 5 factors that control suspension rheology in decreasing order of importance. And they are 5 factors. Colloidal behavior is the most important because you can change the interaction between the particles by orders of magnitude. Particle concentration is second, probably the most abused. Particle size and distribution, particle morphology or shape of particles, and then rheology, the suspension medium, which was added just because I had to talk once in an injection molding conference, and it turns out rheology, the suspension molding medium is important. Usually for us, it isn't. We get something not unique, but special in clays, and that is called thixotropy. And thixotropy or thixotropic behavior is that as you shear that material, the viscosity decreases. So if you have a clay suspension, say a body, and you come into the lab or the studio, the body's set overnight in water, typically it's mixed. You come in, usually it's high viscosity. Depending on a number of conditions, you can often take your spatula and stand it up in the clay bucket, in the suspension bucket. And what has happened is that the clay particles have formed this 3-dimensional network because of Brownian motion, and ideally you would expect that faces and edges stick together. Now they call that a house of cards structure, and reviewing a paper right now that's we've referenced in this house of cards structure. I'm not sure that I'm convinced that occurs. And you could say, well, you know, you don't know everything, which is absolutely true, but we've worked with a lot of people, and there was a guy, Ed Sayre, at the first Science Wireworks conference in 1995, And he said, and I asked him, he'd been working in the clay industry for like 30 years. He was a clay mineralogist by training, highly educated guy. And he says he had looked for this house of cards structure for 30 years and never found it. Does it exist? Not important necessarily, but it's rumored to exist. When you start stirring that material, though, what happens is the clay particles, which are randomly oriented, start to align. And when they start to align, you end up with this viscosity dropping. And the more that those particles align, the more the viscosity drops. Okay? So it is a time-dependent change in viscosity, and that is called thixotropic behavior, or thixotropy. Right? So you'll see that your rate dependent or rate thinning, but that the suspension appears to thin with time. Interestingly, if you take that clay suspension that you just stood your spatula up in and you mix it up, and you stop mixing, it doesn't appear that anything happens. And it will slowly regain that structure. And it might take several days to get back to that structure where you can stand a spatula up in. It's not instantaneous because all these particles then that are randomly oriented then will slowly go back, or that are aligned, will slowly go back to randomly oriented. And as they do that, the viscosity will increase. Okay? Newtonian, always talked about, rarely observed. All right, so water, alcohols, silicon oils, for example, motor oil, those sorts of things, typically are Newtonian. Pseudoplastic behavior is rate thinning but time independent, which is good for us for advanced ceramic suspensions, like for alumina, but not for clays, typically. Dilatant. Dilatant is when viscosity increases with increasing shear rate. So dilatancy, you would see if you go to the beach, for example, and you step, so you have the sand and you have water here, okay, and your fishies are out there. And then here is saturated, and in this region it's just saturated and this is dry. If you walk in this region right at the edge of the water, when you step down, you have your shoe, if you will, and you'll get a discoloration around your shoe when you step, and that discoloration is because you are pushing on the clay part, on the sand. Sand particles are very tightly packed, and water, meniscus, forms the space between. When you shear this, for it to move, these particles have to get out of the way, or the system has to dilate, expand to allow that rearrangement of particles. So when you step on this, the discoloration is that the particles are trying to move, and the water gets sucked into that structure. So the discoloration is water being removed from the surface into the interior. You are exceeding, when you step on it, the rate at which the particles can rearrange. So therefore, the system locks up and becomes hard. And if you stand there, and you stop, if you're not shearing actively, just standing there, then that rate provides room and time for those particles to rearrange. And then you will slowly sink into the sand, right? That's dilatancy. I get calls occasionally from people that say, we have a problem and our suspensions are thixotropic. Don't know why, but there's a tendency to confuse thixotropic and dilatant behavior. Clay suspensions are always thixotropic. No one cares. They care, though, when you have a suspension and you push on it and it becomes hard. Because now pumping becomes a challenge, right? So originally, I thought it would not be possible to create dilatant suspensions with clays. Turns out you can. And the way that you do that is that if you make a clay suspension that is plastic, so you have just enough water to get a plastic body, it doesn't flow. If you then add dispersant to that with that same amount of water, that material will become dilated. So we have two requirements for dilatancy. To be dilatant. One, high solubility. So like in this case here with the sand, there's no room for rearrangement. And two, dispersed. If the system is highly loaded and not dispersed, it will not be dilatant, it will be plastic. So plasticity and dilatancy are actually quite close together. Okay? Thixotropy you see in suspensions. Okay? That same suspension, if dewatered, so you reduce the water content, that same suspension will become plastic. Okay? Rheopectic is interesting Rate thinning with time, or thickening with time, if you will, and rate thickening. Odd behavior, all these I consider to be reversible. So people would argue, oh, rheopectic is like cement paste where it sets. I don't find that to be reversible, so I don't think it qualifies. If you think about the rate dependence for thixotropy, you have a shaped particle with an aspect ratio that will align in the shear field. Okay, rheopectic must be something similar. That alignment is disrupted or something as you increase rate with time. Let's skip this. We have apparent viscosity, okay, which is what we measure, and it is this relationship. If I were to look at shear rate versus shear stress, so what I have is I have something like this. I have my fluid, and I'm shearing it, and I have then shear rate. So essentially, we looked at this way: stationary plate, and I have a gradient. Okay, so this is velocity, but in the x direction. This is my difference, dy. So with this velocity, d vx dy is equal to shear rate. If I take a system of solid system, right? I have a solid, and I shear it, it will deform like this. Good. So you get I think this is your shear strain, gamma, and you have a shear stress. So you get shear stress and shear strain. So for this line is the shear modulus, G. If I do this with a fluid, I shear it, I stop shearing, those stresses are dissipated instantaneously. So what I have to do then is I have to shear this at a rate. So I have to continuously shear that. What I get then is my shear rate, my shear stress. So for this line is viscosity. So shear stress is equal to viscosity times shear rate. Good? So the way that we measure viscosity is we go to a specific shear rate, okay, velocity with regards to distance, and then we will sit there and look at how much shear stress is required to maintain that shear rate. We get a point, okay? Now what we would do is extrapolate that back to 0, and the slope of this line is my viscosity. So we'll call this gamma dot 1, okay? And this is viscosity 1. If I have a suspension of particles, let me rephrase that. If I'm Newtonian, it's like water, then all the points fall on this line. And I have one viscosity regardless of shear rate. Okay, so that means that my viscosity is independent of shear rate. If I have a particle suspension, though, and I start to shear it, then what will happen is, if I go to, say, a different shear rate, I would get a different shear stress, shear rate pair, and I get a different viscosity, A to 2. In this case, A to 2 is greater than A to 1. Okay? So my viscosity at lower shear rates tends to be higher. The reason is that I'm reporting these values because that's the way I collect the data. I get shear stress, shear rate pairs of data, and from each of those pairs I calculate viscosity. That's called an apparent viscosity. If you connect the dots, you're going to get something like this. Typically, and I drew it as a curve here. Okay. If you do it on a broader scale, it looks like this. Typically, shear rate, shear stress. Okay. There is a period down here, a region where you have a critical shear stress is how they look at it, like this. Tau sub 0, that's called a yield stress. And most of my materials exhibit a yield stress. Most of the suspensions do. Tomato ketchup, for example, perfect example of the yield stress. Right? Turn over, nothing happens, and then you bang on the bottle to entertain your friends, and suddenly it goes. Right? You can break up that suspension much easier by taking a knife or something else and stick it in the bottle, break up that suspension structure, and then it flows just fine. Okay? But what happens here is that I have then a change in viscosity with increase in shear rate, and that gives me shear rate thinning, because I'm looking at these sets of data, okay, A to sub 1, A to sub 2, etc. And this statement here on the slide seems a little bit odd, Viscometers do not know what has happened before. We are now living in a world where I can program the viscometer, it collects a bunch of data, but it never, looks at the previous data point and decides what to do next, right? You program it to do something. In the end, you can go back and put all that data together, but it's going to give you a series of shear stress, shear rate sets of data and calculate that viscosity. That's an apparent viscosity. So, in this example, with the yield stress, what happens is, if I look at this little region down here in the circle, and I draw that larger, it comes up something like this, and then it curves over. Shear rate, shear stress, and this region is actually what I've drawn here. Okay? What you see down here at very low shear rates is you essentially have Newtonian viscosity. Very high viscosity value, okay? And then we approximate that, say that is eta sub 0. And then once I get past some critical shear rate value, then we start to see that the viscosity values are changing, right? With higher shear rates, my viscosity is then decreasing. And if I take and I plot all of this data, what I get is a curve where I plot log of viscosity, log of apparent viscosity versus log shear rate, and it looks like this. So at very low shear rate, this is a log scale, right? So at very low shear rates, I have Newtonian-like behavior, meaning that my viscosity is independent of shear rate. Here's eta sub 0. This is eta, which is a function of shear rate. Here is eta infinity, where I get out far enough that my shear rates are very high, and my viscosity values then converge to a single value, and I get a Newtonian plateau. This is invented data, but it's the same idea, okay? And then to illustrate the point, right, there's 5 orders of magnitude on the y-axis, and there's 8 orders of magnitude on the x-axis. I mean, the idea is that it is orders of magnitude difference getting from our shear rate and apparent viscosity. So at very low shear rates, you get an eta sub 0 value, okay? That would be the equivalent. The reason it's important to us is if I do slip casting, for example, right? I make up a suspension, I pour it in a gypsum mold, then what do?
Wafers.
Wait. I walk away. What's the shear rate? Not a trick question. What's the shear rate in the mold? It's 0, right? So the viscosity of that suspension in the mold is very, very high. And then when I take that mold and I'm done, I get the wall thickness I want. From drain casting, I invert the mold and the slip runs out, suspension runs out. Now I've just gone to a higher shear rate, right, by doing so. And then I exploit that shear rate thinning behavior so that it can clean the mold out. If I wanted to create really high quality slip cast wear with a nice smooth surface on the inside, for example, and no drips, what I might do is engineer my shear rate thinning behavior to be a much larger difference in viscosity when I break that network and start to pour it. Okay? We proposed that years ago, and it didn't get funded for us to check it out, but I believe you can independently change that shear rate thinning character and viscosity so that you could actually engineer bodies to be very good at drain casting. Okay? But it goes from the 0 shear rate, high viscosity, to a shear rate thinning regime, and that's when you pour the slip out. Okay. Now, this curve is interesting because what happens here, if we go back to our dilatancy, at some point here, the viscosity shoots up. Okay? What that gives us, this is dilatant here. Okay, this behavior is dilatancy. For clay systems and for plastic forming systems, this is fascinating. All right? And what I get here is at some point I get what's called a critical shear rate. Okay? And my critical shear rate, all right, if I get past a certain shear rate, the system will lock up. So I'm shearing the material so fast that the particles do not have time to rearrange, okay, and they will lock up. We actually see this in forming processes. So this behavior here for plastic bodies, this is also a Newtonian region. We would propose that that's what happens for plasticity in porcelain bodies. And if you shear the material too fast, okay, such as in a automated jigger or a ram press potentially, you can get to the point where the clay will tear because it can't react fast enough. And that's a common forming defect that has to do with machine setup and the character of the clay. We can extend this region by changing salt concentration. We'll talk about that as we progress. We're covering a lot of ground at the moment. We're going to come back and deal with these things later. Okay? So let's talk about colloids really quickly. Okay? I have small particles. Small particles are defined as colloids if the Brownian motion dominates over gravity. So what I have is, I have a particle in suspension, gravity causes it to want to settle. Okay? Depending on size, Stokes sedimentation, you can go through that if you wish. Large particles want to settle. Small particles settle more slowly. Okay? So if I have a small particle, it will settle less quickly than the large particle. Now, if the particles are small enough, what I have this particle is very small, sitting in say, a suspension medium, and molecules in the suspension medium are randomly impacting this particle. And if you get more molecules on one side hitting the particle at the same time, you will translate the particle. It will move. I do this intentionally that way. Okay? Statistically, right, there's a probability that you'll have more molecules of water hitting one side of the particle than the other. Particle moves. Okay? It has two types of movement. You have translational, right, which is something like this, where the particle actually moves, and we look at this distance. It's called x bar. Actually, the average distance the particle moves in a given period of time. You have another type of motion for the particle, which is rotational, particle spinning. Okay. Now, interestingly, particles flocculate and they stick together. They don't actually stick together like this, where you have two particles, for example, touching. That's actually relatively rare. They actually typically stick like this, with a small separation between the particles. If you take suspension of particles, okay, and you put them in a microscope slide and you look at them, if you have sufficient magnification on the microscope, you will see that the particles are sitting there and they're vibrating. They're not stationary. They are actually both vibrating and at the same time, you can't see this typically, they're spinning around, right? Do we care? Turns out we do. If we add a dispersant into this system, for example, something that's going to absorb on the surface of the particle, and the particle is sitting here spinning around, right? Then the dispersant comes in and coats one side, and the particle is spinning around. As it spins around, the whole particle gets coated and spontaneously deagglomerates. It's a slick system. It actually happens if you go faster. It's nearly instantaneous. Same thing with pH. I change the pH of the suspension. My particle isn't stagnant, and one side reacts and the other doesn't. Since the particle is constantly moving, those reactions are called fast ion reactions. They occur very rapidly. The attraction between the particles, though, is dictated by something called the Hamacher constant, which here is called A effective, and this is the Hamacher constant. Okay? And the Hamacher constant dictates the magnitude of the interaction between two particles. It's the attraction force between the particles. If the particle is small enough, in Brownian motion, that's what this is called, Brownian motion, if Brownian motion dominates behavior over gravity, then we would call this a colloidal particle. So that means that the interaction between the particles is more important than sedimentation behavior. We call them colloidal particles. In our suspensions for porcelains, clays are the colloidal particles. Quartz and feldspar are simply too big. And if you wish to demonstrate that, it's very easy. Take quartz particles, put them in suspension, mix them up really well in a graduated cylinder, set them there, come back about 3 minutes later and they're settled. All right, maybe 4 minutes. Okay, doesn't take any time at all. Put clay particles in that suspension, you can come back 10 days later and they're still not settled. Some will settle. My Einhoff settling cones, for example, show you that. But I will still have clay particles in suspension days later. The big particles will settle out. That was the idea behind the separation of particles by mineralogy. By setting them up based on size, they will settle out, and I can separate them that way to see how that works. You may be familiar with Faraday. He does gold colloidal suspension particles, gold colloids in suspension that have been in suspension for 200 years, or 150 years, or it's been a while, okay? But you can go see them in the Faraday Museum in London. A lot of people stand at the doorway for that one, okay? So as the particles get bigger, that van der Waals attraction increases. So what you have here is your separation distance between the particle and particle size. You can calculate then that as the particle gets larger, that attraction potential gets greater. That's fine. So bigger particles have greater attraction. But that attraction is small compared to gravity if the particles are large enough. So then it becomes unimportant, okay? And so this is just showing you the effect of particle size on that attraction potential, and we divide it by kT. So this Brownian motion is really related to thermal energy, Boltzmann's constant times absolute temperature. And what we say is that if the van der Waals attraction is less than or equal to 10 times thermal energy, the particles will spontaneously be agglomerated. Okay? There's a potential for that. As the interaction between the particles is less than this value, like if it's 2 kT or whatever, then the particles will come together and stick, and then they spontaneously de-agglomerate. Okay? If it's greater than 10 kT, then they come together and they stay together. The Brownian motion is not sufficient for them to de-agglomerate. So to give you an idea of magnitude, two things. If I put a medium in between the particles, and that medium is polar, for example, even if it isn't, as soon as I put a medium other than air between the particles, I reduce that attraction potential between the particles. So I see a reduction in the Hammurabi constant when I go from air to water. And water is great for us because the polar nature of water really helps the surfaces to react and reduces the Hammurabi constant. So alumina in air is around 15 times 10 minus 20 joules. In water, it's 5. So it reduces by a factor of 3. Fused silica, roughly a factor of 7. Okay, reduction when you put it in water. And quartz, you get a reduction of roughly a factor of 5 when you put it in water. Okay, so that means that if you take your powder in air, it's going to be fluffy. You put it in water, and that it suddenly reduces that attraction potential between the particles, and it's easier to work with. We like that in clays. Dig clays out of the ground and put them in water, they're immediately plastic, right? They're immediately work. The Hammurabi constant for kaolinite is small compared to alumina, and a little bit larger, but similar to quartz, okay? What that means is that clay and water is, by and large, self-dispersing, okay? You put it in water, the attraction between the particles is small. The benefit of that is as you dig it out of the ground, that material can be worked with. If we were to go say, let's say you go find, if you found alumina in the ground, you want to work with it, doesn't work well by itself. You have to do a lot of things to make that work. If you take clay, it is intrinsically plastic. It's intrinsically easy to disperse that material. Okay? That has helped us to work with clays, and frankly is the foundation for civilization if we look at it that way, because you can take something out of the ground, you can make something that, you make a tool. You can laugh about the idea that a bucket carry water is a tool, but it is definitely a tool, okay? And it changes then, the ability that you can pull that clay out of the ground and use it is important. And then you find that some clays work better than others. So what are we going to do next? What we want to do is we want to overcome this attraction force between the particles. Okay, and to do that, we can bring in one of 3 mechanisms for dispersion. Okay? One is electrostatic. We can change the pH, create a charge on the particle surface. And if I create a charge on the particle surface where the particles are all, say, positively charged, if that magnitude of that charge is great enough, these particles will spontaneously de-agglomerate and not stick back together again. So that's electrostatic stabilization. That's a change in pH. We don't really like to do that for clays for a number of reasons. One, most important probably is, nobody wants to work with the concentrated acids or bases necessary to impart a charge on the particle surface sufficient to disperse. Okay, so you have a lot of surface area in clay. So I think I mentioned it the other day. If I have, say, kaolin from Georgia, I get something like about 25 meters squared per gram surface area. So if I bring in a reactant, I have to bring in enough reactant to essentially react with that amount of surface. So let's say I'm at Buffalo, China, and I have 30, well, how much clay do I have in a batch? Buffalo, China's clay amounts in the batch are about 35%. Okay? So if I bring, let's say, Buffalo, China, their batch size was 30,000 pounds. And to that, they added 20,000 pounds of water. Okay? So they had 50,000 pound total batch weight. 30,000 pounds, 35% of that is clay. You have to convert pounds to grams and multiply it times 25 to give you your surface area. Let's see. That's a boatload of surface area. Not no value. Okay, millions of square meters probably. So you have that value, and now you need to bring in something to react. If you wanted to change the pH with that much surface area, you would have to add in essentially either a lot of, say, 6 molar, which would be ridiculous, or you go to the most concentrated acid or base that you can find, because you're going to add it, nothing will happen. You're going to add it, nothing will happen. You're going to keep adding until you have reacted all of that surface. And so nobody wants to do that. So instead, what we have is we go to electrosteric stabilization. We go to something like either sodium silicate or sodium polyacrylic acid. Or polymethacrylic acid, or sodium hexametaphosphate, or whatever. These are electrosteric stabilization. Okay, so electrosteric stabilization, what I do is I bring in a polymer that has a charge. Now I have the same amount of surface area, that hasn't changed. But I bring in PAA, for example, polyacrylic acid, looks like this. This carboxylic acid group, we write this as an R and a C, double bond O, single bond O. This gives me a net negative charge, and I bring in a sodium ion to associate with that charge. So I get a sodium ion here that associates with that charge. I have N, so this repeats. And I end up with a long chain, relatively long chain. For PAA, my molecular weights are somewhere around 8,000. Okay, so what does that mean? If I do the math at 8,000, so molecular weight for this chain is about 8,000, okay? That means that N, my repeat number here, is about 150. So that means I have a chain, polyacrylic acid. I have a chain, a polymer that has, maybe, if all is associated, I would have 150 charged sites on that polymer chain, okay? I didn't draw 150 marks, you probably already realized that. Okay. But that I have essentially these little ribbons or strings of charge. It is the perfect setup. So what will happen is that we have our particle, and the particle, I'm just going to draw it around. The particle comes in, right? And I put the polymer absorbs on the surface of the particle, makes the particle net negatively charged. What's the benefit? Oh, I've got my 50,000 pound batch, 30,000 pounds of raw material. My 30,000 pounds, if I take that times 35%, I'm roughly, say, 11,000, 12,000 pounds of clay times 400. Okay, I just lost the math. So, and then look at the surface area. I have a huge amount of surface area. I can bring in a gallon bucket of Darvan in solution, dump it in that vat, and instantaneously my viscosity drops by orders of magnitude. Because that polymer now is specifically associating with the surface of that clay. And it's safe, it's effective, I control that viscosity readily by simply bringing in dark. Or sodium silicate, okay? Sodium silicate is preferred. You also have sodium hexametaphosphate, which they say H, hexametaphosphate, shrimp for some reason, okay? That's another one, and that was common. I'm going to ignore the double layer model, and I'm going to ignore the ion strength effects at the moment, and the LVO 30, and we're going to go to here, okay? Now, I have an interesting problem. Let me do this first. Let's go here. Okay. So, this is how suspensions behave, the rheology of these suspensions as a function of my dispersive level. So at the bottom, you will see this is the concentration of dispersant in milligrams per meter square. Okay? So I've corrected my dispersant addition based on the surface area of the powders in the system. Now, this is a porcelain batch. So I've got clay, and quartz, and feldspar. When I do the math, 95% of my surface area is with the clay. That's it. There it is. Okay. So I said 35%. I was wrong. It's 36%. Sorry. And so kaolin, EPK, 27 meters squared per gram, measured surface area. Ball clay, 26 meters squared per gram. Close enough? All right. Nepheline cyanide, 1.1 meters squared per gram. At this time, later on, that value we measured 2.5 meters squared per gram. Not particularly important. Okay. Quartz is about 1 meter squared per gram. Aluminum is about 1 meter squared per gram. This is Buffalo China's batch, essentially, except EPK was actually in their batch, tile kaolin number 6. No difference. Add it up, okay, and then look at the amount of clay that you have in the surface area from the clay. 95% of the surface area in the batch is brought in by the clay, even though it's only 35% of the batch. Okay? So the other particles are there, but they're not participating in terms of dispersion. It's just not important. For one thing, even if they were, if my PAA would absorb on the surface of quartz, which it will not, I'm still only taking a really small amount of PAA out of that system, polyacrylic acid, to interact with the quartz particles. Okay? Alumina, yeah, you can say the alumina is participating, but it's a really small contribution. So rule of mixture, if you calculate the overall surface area of the batch, and it's going to be roughly somewhere around 1/2 of 26, a little bit less, probably somewhere around 10 meters squared per gram. Okay. So overall, my dispersants, there were 5 of them. Sodium polyacrylic acid, sodium polymethacrylic acid, sodium hexametaphosphate, sodium silicate, soda ash, and then a blend of soda ash and sodium silicate. Here's what happened. When we first started doing this, the problem, I mentioned that I went to Engelhard in Georgia because they were having a problem with these little particles sticking to the doctor blade and the clays making paper. Remember that discussion? Okay. They didn't make very many of these little particles, but when they made them, it was a problem. And we think that the problem was that sodium hexametaphosphate, they went to sodium hexametaphosphate as a dispersant in the clay system. So the way that industrial clay processing works, this is before we get to porcelain, okay? Let's go back a step. What's the impurity? What's the mineral impurity in clays? What's the mineral impurity in clays? Anybody? At mine clay other brown, what's the biggest mineral impurity? Quartz, right? What's the problem with quartz? Big particle, right? You're making clays for the paper industry. The particles, big particles of quartz get in the way of the coating process. Okay? Your customers don't like them, and if you don't take them out, and your competitor does, then they won't buy from you. They buy from your competitor. So they want to take the quartz out. How do you take the quartz out? Well, you have the clay suspension, and you have the quartz particles all in suspension, but they're agglomerated. So what you do is you disperse the clay. Quartz particles are then free to settle out. If you don't disperse the clay network holds the quartz particles in place. So you can't separate them out. So they disperse the clay to remove the quartz. And they found that they could save a little bit of money. This is the bane of industry. They can save a little bit of money by going to sodium hexametaphosphate. In the process of doing that, the sodium hexametaphosphate, okay, this sodium is listed there improperly. It says NaPO, what does it say? 3. It says 6 here. Okay? The idea here is that this will give you a sodium plus a PO3 minus anion. This is a complete fallacy. Not the way this works. Okay, it's a simplistic view. But what happens is sodium comes off, and then I have impurities either in the clay or brought in with the water, and that big impurity is calcium. Okay? And the calcium bonds with the phosphate anion and creates insoluble calcium phosphate. Okay? And it's what happens. It turns out that insoluble calcium phosphate is remarkably sticky. If you go in the lab and you take phosphoric acid, put in water, and add calcium chloride, you will form a residue that's almost impossible to get off the beaker. And it is our hypothesis that those were the particles that were forming that disrupted the clay coating process for these calcium phosphate particles. As a result of using sodium phosphate as a dispersion. At this time, sodium phosphate was sold commercially as Calgon. Okay? And Calgon is water softener. You add it with your soap, okay? And it ties up calcium. Oh, wait. Calcium gone. There you are. Okay? That's Calgon. So the sodium hexametaphosphate, if you use sodium hexametaphosphate, it's a great dispersant for clay systems. Okay? So there are two types. This, plus our sodium hexametaphosphate, would be an inorganic dispersant, and this is an organic dispersant. Okay? So, sodium hexametaphosphate, sodium silicate, and then we have soda ash. Oops, spell that right. Sodium carbonate, soda ash. Put it in water, dissolves a little bit. That's good. We have a problem. Here's the problem. Is that an article written by Johnson and Norton, I believe, in the 1940s, looked at different dispersants, and they looked at sodium salts and calcium salts, and looked at how they work to disperse clays. What they found was that salts that contain sodium were much more effective at dispersing clays. Okay? Does that make sense? I will post the article for you on campus. So, what happened is that result got misinterpreted to suggest that the sodium was responsible for the dispersion of clays. That make sense? Sort of, except it doesn't. Okay? So, what Johnson and Norton concluded was that the anion, this is what they stated in their article, which is correct, the anion is responsible for dispersion. But the cation would dictate the effectiveness of that dispersant. And the reason is, if I put sodium salt in water, it tends to dissociate better, it dissolves better. If I bring in a calcium salt, it doesn't dissolve. So then if I bring in, say, calcium silicate as a dispersant, it stays as a particle and doesn't dissolve, and therefore I never get the silicate ion in there to help me disperse the clays. Make sense? So, the industry, though, decided that sodium was a dispersant. Okay? So the first conference I went to having to do with clays was a meeting, I don't remember where it was. And we did a lot of colloidal behavior and colloidal chemistry, and they liked the sulfate ion. So you have gypsum, calcium sulfate, you put it in water, and it dissolves. Okay? And so what they developed as a clay characterization tool is called sulfate ion test. So what they were looking for was to determine the amount of soluble sulfate in the clays. And they had correlated rheology with the amount of sulfate, but you should recognize that that correlation was not very good. But they said, well, if we could determine the amount of sulfate in the clay, then we can predict the rheology of those clays potentially. So they do it as a soluble sulfate test, and they bring in barium carbonate. Barium carbonate dissolves, and it gives you a barium 2 plus a carbonate 2 minus. Right? So what does that do? Oh, well, the barium then will associate with this sulfate to form an insoluble barium sulfate. So what you do is you mix this up with barium carbonate, and then you measure your precipitate, and you go, look, I can tell how much sulfate's in this system. Okay? And then use that to correlate with the clay rheology, which it marginally does. So now what happens is that they're adding the sulfate and adding the sodium into the system, and they said, well, sulfate's my problem. So there was a talk given where they correlated rheology with sulfate level. They showed that as the sulfate level went up, the viscosity went up. And they changed the sulfate level with calcium sulfate. So I was young, and my tachometer was clearly not working. I raised my hand, I said, how did you change the sulfate level? And I said, well, we added calcium sulfate. And I said, do you think the calcium had anything to do with it? And he says, no. I said, well, if you do the same test with sodium sulfate, you'll get a different result. What's the answer? Well, of course, sodium is a dispersant. Okay? Here's the problem. Clay particles are negatively charged in water. Okay? That means the anion, okay, it means the cation, by the way, is a counter ion, and it is then compressing the double air and causing these suspensions to coagulate. So sodium is actually a coagulant, not a dispersant. We're going to come back to that in a minute. I will show you the dispersion curves, and then we'll talk about the colloidal nature of kaolinite, probably on Monday. Okay? So here's our suspension. What you see is pair viscosity on the y-axis on a log scale. All right? These are Pascal seconds, 0.01, 0.1, 1 Pascal second, 10, and 100. And then the x-axis is dispersion level in milligrams per meter squared, so it's corrected for the surface area of the particles. What you see is with a relatively small addition, around 0.2 milligrams per meter squared, we drop our viscosity by 1, 2, 3 orders of magnitude. So I go from essentially sour cream to milk. All right. Notice that sodium carbonate, I see a marginal reduction in viscosity. And the reason is that this carbonate ion that comes off of that sodium is bonding with calcium to take calcium out of that suspension. So calcium is working against me, okay? But if I bring in carbonate, I tie up the calcium. When I do my test for barium carbonate, I'm bringing in the barium, ties up the sulfate, but the carbonate ties up the calcium. So I'm cleaning up my ions in suspension, okay, that are affecting my viscosity. It is common in the industry to add sodium silicate plus sodium carbonate in a 1-to-1 ratio. And presumably it's doing that to clean up the water and to make the dispersant more effective. But in fact, right, carbonate is not necessary. But the perception is because of the sodium that it works well. So if you blend these two suspensions together, basically the dispersant is dominated by having the particles undispersed with sodium carbonate. When you get to this point, you have excess dispersant viscosity, then follows the sodium silicate curve. So the carbonate isn't actually doing much to help that suspension behavior. There's another misnomer, by the way. I wrote this as Na2SiO3. That's not the ratio. So what you get is an oligomer. You get a polyanionic silicate ion, which just has multiple charges. That is something similar to what we see with PAA. And we change that ratio of sodium to silica and how that material is precipitated. So here's where we are. We are on time. We are going to do this. I will post an article for you called The Colloidal Nature of Kaolinite. Okay? It talks about the structure of kaolinite and what's going on with kaolinite. And I think this is in your homework. Is that true? I believe it is. Okay? So we have the colloidal nature of kaolinite. That article would be posted for you on campus. Okay? And then you can read it. And it talks about how structurally the surface chemistry differs from one side of the clay particle to the other. okay, that follows the structure of kaolinite. That's important for us because it tells us why our dispersion demand is different than what you see for aluminum. Okay, I believe this is homework 3. All right, questions? See you on Monday.
Measured LOI is 14, and so if you do it this way, it'd be like 100, so it wouldn't have any.
Correct.
Okay, all right, I wasn't sure. So when it's the LOI and not the chemistry, you always use, you assume it's just, okay, it's always 13.96.
Right, so if you put that over, the reason that LOI
Oh.
the reason that this is greater is because this contains mock If you recall, mock realnite has that structured water layer. And the LOI for mock realnite is greater than the LOI for kaolinite.
Oh, because you have the water within it.
Water. Right. So the consequence of that is that there is a, you actually can get a higher LOI from mock realnite than for kaolinite, but there's a blend of the two. There's almost no free quartz in EPK, so that makes that chemical, that LOI value creep up above 14.
Gotcha.
So you would say that you might flag EPK and say, doesn't work, or you might say that it appears that there's no free quartz.
Right.
Right, but you have another mineral species that uses water, that has more water in it than kaolin.
Which is why it goes up. Because like when I did the chemistry, I think it was like 7% or something. Ish, which then I thought was kind of like high.
Yeah, 7% or what?
Like 7% free quartz. When I did the chemistry version.
Yes, right. The reason is, it's not high, but the reason is that we made an assumption, right, that you have kaolinite and quartz, but you have kaolinite plus smectite, maybe quartz. And if you did a rule of mixtures for the fraction of smectite and you knew its LOI versus you could calculate
And it
that.
would probably go
Right.
down.
And then you obviously, but that requires quite a lot of other work that we haven't been doing.
Right.
But the rest of them all work really well as a way to approximate.
Okay,
the
yeah, I
quartz.
did notice the other
Right.
because I did a few more.
So
Okay.
in essence, EPK is an anomaly, if you will, in
Okay.
terms of this, but it isn't really, but it's just that is why EPK works so well as a glazed suspension
There's
glaze,
no-
because of that smectite. So that 2-to-1 sheet silicate helps suspend large particles in suspension, right? But without an idea of how much is there, I need a smectite that I can get an LOI value for. It's someplace around, I think it's around maybe 18%. It can be really high.
Oh, wow.
Because you're talking about a lot of water in between,
Right.
plus water in the
Actually,
within the 2-to-1
Yeah,
sheet silicate.
yeah,
There's a small
yeah.
amount of water there. So, but that layer of water. So the way that we would do that is we should do TGA on EPK.
okay, yeah.
Because you would see that the water loss associated with water in between the layers,
Okay.
and then the water loss associated with what's in the structure.
Okay.
Are you taking thermoanalysis in the vivo?
I mean, I wasn't planning on it, but maybe.
Maybe you should.
Maybe I should.
Well, I think it would be really informative. You said you did it some in your work.
Yeah.
Yeah,
So-
it's really useful, and I think it should be in our curriculum. We're working on getting